Good evening and welcome to tonight's virtual program. I'm Emily. I'm one of the librarians here at the Rockland Public Library, and we're thrilled to host Madison Smith tonight in collaboration with the Camden Conference. A couple quick programming notes before we get started. Upcoming programs next Thursday, January 14th, we have author Earl Brecklin, and he'll be presenting a talk on his new book, Wild, Weird, Wonderful Maine. He'll be sharing some of the people, places, things, and events that define Maine's quirky spirit, and it promises to be really fun. The week after that, on January 21st, we'll be hosting author Lori Chandler, who will discuss her new book, Through Woods and Waters, about her time canoeing the Katahdin Woods and Waters National Monument, and some of her other solo canoe journeys. That's it from us, and I'm gonna turn it over to Susanna, who will be introducing, Jane, who will be introducing the Camden Conference.
There you go. Now I need my video on. Sorry, folks. I was being very polite and turned everything off. Hi, I'm Jane Nice, and I am working as the volunteer chair for the Camden Conference Community Events Group, and very excited that we are here, thanks to our host, Rockland Public Library, for making this possible. The Camden Conference is a nonprofit, nonpartisan citizens forum driven almost exclusively by volunteers from our community. The mission is to foster informed discourse for global issues. And in keeping with that, we offer a series of free community events leading up to our annual conference in February. And these are up and down the coast of Maine. And you know, with this unusual year, you could look at our events calendar to see events that are on Zoom and therefore available to you no matter what the date, no matter where you are. You can get permission, ask for permission to join. I would also like to say that if you see titles that and speakers that you would like to hear and see after their date, they are recorded and therefore available when you look at our calendar, the news. In the news, you will find all of the available links for pulling up some of our events, most of our events going back to the beginning that have been recorded. So we're touching on areas, as you can imagine, that are related to our February conference theme, and they may not be covered during that two-day format. There's so much to talk about in the Arctic from every single angle that you could imagine. So please take a look and see if you find one of those community speakers, all who are well-versed on some of the topics that you might think of that couldn't get included for the two-day format that we have this year. Now, our speakers' views and opinions and positions expressed are theirs alone and not necessarily reflecting those of us at the Camden Conference. Some years it's more relevant than I think this year, but keep it in mind. This year's conference, which is our 34th, is the geopolitics of the Arctic, as you see in front of you, a region in peril. And it will take place virtually on February 20th and 21st. So this next month, and it'll be live streamed. So it will not be Zoomed. It will have the same quality of live streaming that you would get if you were watching a movie, and a highly orchestrated, shall we say, series of meetings and presentations across the weekend. So it should be fun, and it will be available, of course, as you could imagine, it will be recorded and available at some point. But to get a ticket, the tickets are available for $150 for the weekend for you to pick and choose when you want to see any of the segments that are included in this. For looking at what you need to do is really look at the camdenconference.org. It'll show you the complete speaker lineup. and further information on the membership and conference registration. So you can, it's going to be amazing, and you and your household can, as I said, get a ticket for the entire weekend for $150. And we really, really hope that you will do it. The people that are speaking are coming from all over the world, as we have every year in our themes. Global issues call for global experts. So we appreciate any support you can give us by getting a ticket and joining us at something that should be chock full of amazing experts and speakers. And again, the audience is us. We get to call in our questions and, you know, delve into that with those experts. So it's well worth it, a very interactive experience. So I'm going to turn it over right now for the speaker's introduction to Susanna Hancock, who has worked with us on the conference community events committee. Thanks.
Hello and welcome again. I have the great pleasure this evening of inviting and now the honor of introducing Dr. Maddie Smith to speak with us. Maddie is joining us this evening from Seattle, where she is a postdoctoral researcher at the Polar Science Center at the University of Washington. Motivated by the loss of sea ice in rapidly changing climate, she is currently working to understand how sea ice interacts with the ocean through observations and modeling. Her fieldwork has taken her to the oceans at both ends of the Earth. Most recently, she was a participant in the summer leg of the year-long Mosaic Expedition. The Mosaic Expedition was a collaboration of decades of planning and 20 nations to freeze a research ship in the ice of the Arctic Ocean for an entire year, the largest expedition in polar history. Although Maddie is from Northwest Washington State, her love of the Arctic blossomed about 5 miles from my house here in Freeport at Bowdoin College in Brunswick, where she learned about the Transpolar Drift from Fridtjof Nansen. For those of you who tuned into Annalise Scar's talk in December, this might be some familiar topic. At Bowdoin, Maddie received her undergraduate degree in Earth and Oceanographic Studies and Environmental Science. Maddie returned to Washington to complete her PhD in Civil and Environmental Engineering, where she explored the role of surface waves and turbulence in the Arctic Ocean. Outside of her professional interests, Maddie enjoys cooking and being outside through activities like biking and running. After Maddie's presentation, we'll take questions, so please feel welcome to add questions to the chat box below throughout her presentation as you think of them, but also we'll take them live at the end as well. So Maddie, thank you so much for joining us this evening, or afternoon for you, and the virtual floor is yours.
Awesome. Thank you so much, Susanna, for that introduction. And thank you all for being here today. It's fun to see some familiar names in the participant list as well. So as she mentioned in the introduction, I was really lucky to get to be a participant of the Mosaic Expedition this last summer. And so this evening, I want to try and bring you all along for part of it to give you a taste for what it's like to be a part of the largest polar expedition in history. And I'm also hoping that I can help give you a better understanding of why we need to do this type of research at this time, and also what we hope to learn from these observations for the future of both the Arctic and our planet. So part of why I'm here today is because I became interested in polar science reading Nansen's journal from his time drifting across the Arctic while I was a student at Bowdoin College in Maine, like Susanna just said. And so in 1893, Nansen began his drift across the Arctic, the first one to do so, by sailing to the eastern Arctic. So you can see on this map here near Russia. And he was planning to try and use what we call the Transpolar Drift to drift all the way across the Arctic and through near the North Pole. And that's exactly what he did over the next 3 years, completing this journey. And along this journey, he made countless observations of what was happening in the ocean and the atmosphere and a lot of the features of the Arctic system. And a lot of the work he did really set the stage for a lot of things that we now know in polar research, our understanding of how the ocean moves, including the transpolar drift and the animals that live there. And so that was a big inspiration for me as an undergrad. If we fast forward now to 2019, there have been a lot of polar journeys in the time since Nansen. And there's been a number of scientific and also kind of adventure journeys that have gone from the North Pole. And there's been at least a few year-long expeditions in the Arctic to observe a full year, full seasonal cycle there. But there's still a need to understand the full seasonal cycle in the heart of the Arctic near the North Pole where Nansen went. And so Mosaic is this expedition that has been planned over many decades to fill this gap. And so inspired by Nansen, the plan of this expedition was to freeze an icebreaker into the ice, like Nansen, and use the Transpolar Drift to move across, surrounded by the same ice over the whole year. The icebreaker that is used, though, is much bigger than the ship that was used by Nansen in the late 1800s. So the one that was used is a German vessel called the research vessel Polarstern. You can see kind of a schematic of that in the upper left here. And so working from the ship then allows stations to be set up in a broad area on the ice around the ship that can be continuously maintained over the whole year. Also, unlike Nansen, this expedition also had the support of a lot of other vessels and aircraft. So other icebreakers were used to do transfers of equipment and people throughout the year, as we had the need to include lots of different scientists and people with different expertise. Aircraft were used throughout the year mostly for the science perspective to give a larger scale to the observations that we're making. On the Mosaic website where I got this image from, they say that not only is the science behind Mosaic a huge endeavor, but also the logistics face unparalleled challenges. And I think this is a good point because it was really not only a big scientific expedition, but really a demonstration of a lot of the logistics that can come together with different nations working together to kind of address this big question. Okay, so yeah, I just want to talk a little bit about the motivation for this expedition and why we needed to do it now. The Arctic is a key area of global climate change with warming rates that are exceeding twice the global average. So this map of the globe shows the temperature change near the surface of the Earth from 1970 to 2017. So what you can see is this big red area over the Arctic where there's been, and it represents a temperature change between 4 and 7 degrees Fahrenheit in this area. One result of this warming is the loss of sea ice. So as you probably know to some degree, the Arctic has ice covering the ocean like a lid for much of the year. And so you can see in the satellite reconstruction from September 2010 that there's this ice over the ocean over a lot of the area. But the area that this covers has decreased a lot in the last few decades. So this GIF shows the annual average of area that the sea ice covers in the Arctic from 1979 to 2019. And what this is just showing is you can see the significant decline in the extent of ice extent. It's well possible that the Arctic Ocean will become ice-free in the summer within the 21st century. And the dramatic changes that we've seen and then might expect in the future will really affect our weather and climate across the whole Northern Hemisphere and even globe. And this matters especially because our projections of warming have the most uncertainty in the Arctic compared to anywhere else on the planet. So this figure shows the projected warming for the end of the century, so about 2100, compared to 2005 to 2015. So you can see in the middle here that's showing the warming that's expected around the equator, which is only around which is expected to be around 5 degrees Fahrenheit. I don't want to say only, it's still a lot of warming. But what you'll notice is that in the Arctic, it's much larger. It's projections of warming between 9 to 27 degrees Fahrenheit. And it's not only much larger than elsewhere on the planet, but it's also a lot more uncertain. This is a huge range of warming, and this makes planning and adaptation to this projected warming really difficult. These projections use models that we call global climate models, and they have representations of every part of the system and the planet. So they represent the atmosphere and the ocean and the sea ice. And all these components are really important to understanding and making these projections for future Arctic changes, both in terms of specifically the temperature, which we're looking at here, and then also other details of what the Arctic will look like. So this is really largely the motivation for this massive expedition that was called Mosaic. And I just want to show this quick video because I think it's really nicely done that kind of further explains the kind of general layout of Mosaic and what we really did throughout the year.
Under the direction of the Alfred Wegener Institute, scientists from all over the world are working together and have set up a research camp on the ice. This includes an ROV city, where researchers use remotely operated vehicles, ROVs, to collect observational data under the ice and transmit it back to the surface. There's also an ocean city, where the experts lower measuring equipment through holes in the ice and haul water samples to the surface. There is an ice research camp, where researchers study and observe the sea ice and snow cover. There is a Met City and Balloon Town, where the researchers collect data on the atmosphere and air composition. Up to 50 kilometers around the Central Observatory, several dozen ice monitoring stations have been installed. They drift with the camp, autonomously recording and transmitting measurement data along the way. Additionally, aircraft augment the study of the ice, atmosphere and clouds by taking measurements from the air. Icebreakers from international partners are available to exchange scientists and crew as needed. The overall structure, the Polarstern, research camp and surrounding measuring stations will all drift through the Arctic for an entire year, collecting valuable data. This data will be vital to understanding the Arctic climate and how it will impact the rest of the world.
Okay. Yeah, so I think that video shows really well the kind of this really large scope of the Mosaic Expedition. And so the drift of the polar stern to begin this expedition began in October 2019 on the Russian side of the Arctic, close to where Nansen began his drift in 1893. And it's shown by the orange arrow on this map. And so the ship then drifted with the same ice all the way through the winter and the spring with the Transpolar Drift, actually somewhat faster than we expected, to where the second orange arrow is, which is where I joined the expedition and moved onto the ship at the beginning of June. So we then followed the flow all the way until the end of summer when it reached the ice edge. That's when I got off the ship. The expedition did continue afterwards. They completed the year back further inside the ice edge near the North Pole. And this is the group of scientists and crew that made up leg 4 of Mosaic, which is the part that I was involved in. There's about 100 people here. And there were even more nationalities than the 20 official Mosaic countries that were represented in this group. So it was a really diverse group. And we worked really hard all summer to collect lots of amazing data to understand the Arctic system and sea ice melt. I also just, we of course worked really hard for many months on the ship together, but we lived together on the ship. So I just want to mention that we also had a lot of fun together. We, had parties, made birthday cakes, gave each other haircuts, played music together. So everyone works really hard, but we also have a lot of fun and enjoy each other's company as well. And it's really cool to get to live with so many different people from so many different places. And also kind of on a similar note, the ship is really well equipped and very comfortable to live on. And there's even a gym, which you can see here, but we also find other ways to get out our energy and stay occupied when we have extra time. So here's doing some group workouts on the ship, and then we even went on some runs on the ice. So getting back to the science, as the video was hinting at, all of these scientists on the ship were broken into different teams studying the different components of the system. So though there's definitely a lot of overlap and collaboration between them, we had colleagues that were specifically there to study the atmosphere and the ocean, as well as the biogeochemistry of the Arctic, which is specifically the gases mostly, and then also the ecosystem, so the little things living in the water. And so this is just, this photo shows some of the camps that were described in the video and the reality of what those looked like on the ice. So these different camps, we have here the Met City at the top, which is the atmospheric scientist area, Ocean City, where they're putting instruments down into the ocean below the ice. And then we have some of the ice instruments in the foreground here. And we're all sharing the same ice to understand how the systems work together, but we really collaborate to kind of carve out these different areas to make sure we're not disrupting each other's scientific measurements. So I was specifically part of the ice team, and that group is pictured here on the back deck of the Polar Stern. And we're in this picture, we're holding some of our favorite tools that each of us used to study the ice during the summer melt season and beyond. And this was a really amazing group of people that I feel really lucky to have gotten to work with, representing 8 different countries and people from lots of different career stages and expertise. And I'm in the bottom left down here, and I'm holding 2 of my favorite instruments that I got to use this summer. And I participated in Mosaic specifically because I want to better understand how sea ice melts during the summer. And the project that I'm working on is specifically motivated by understanding these processes because of the needs that we have to better represent them in these models that make projections of future changes. So 2 of the main tasks that I was focused on were looking at the albedo, or basically the reflectivity of the sea ice surface, which allows it to reflect a lot of the incoming light and energy and keep it cooler to slow melting. And then also I was looking at measuring the heat in the ocean. So heat in what we call leads, these are these areas of open water between sea ice, like I'm in the kayak in this photo, there can be a lot of heat here that can actually help to melt ice from the sides and the bottom. And so I'll come back to describing these a little bit more later. So for me, this journey to do the science began in a really different way than I expected. We were set to leave at the end of April. As you likely all remember, the world at that time, we were figuring out how to deal with a virus that had spread to nearly all corners of the earth. And the danger of getting this virus on a ship, let alone one trapped in the Arctic away from evacuation or major hospitals, is really serious. And so all of the expedition participants and crew did a 2-week quarantine in a hotel in Germany before boarding the ships to leave. So the logistics for this expedition were already, quite complicated, but the institution coordinating it, the Alfred Wegener Institute, did an awesome job to make sure that we were able to still do the science, given everything that was going on in the world last summer. So we're really grateful to make it out. So after our long travel there, all the quarantining we did, and a long transfer on a vessel up to the Arctic, we finally made it into the ice, which is what's shown in this video. So this is standing on front of the ship as we finally go from the open water into the ice edge. And the landscape immediately changes with the ice all around us. And this was a really exciting moment for all of us on board. It felt like a big relief and also really exciting to finally be in the ice and feel like we're really on our way to making it to the research camp to do our science. Eventually, we made it to what we lovingly call the Mosaic Flow. So this is a piece of ice that's referred to as a flow. So though the ice may cover the entire ocean for much of the year, it's still made up of lots of different pieces. And so these discrete broken pieces can vary in size and shape and age. And so they picked one of these pieces, one of these flows, in October the year before, 2019. And that's where the research camp was set up and where it still was when we joined at the beginning of summer. In this photo, you can see the entirety of our flow, and you can see some of these research areas near the ship here, which I'm pointing to with my mouse. And so the ice that these are on is typically around 6 to 7 feet thick, but you can see some of these areas of what we call ridges. They look like little hills on the ice, and then there the ice can be up to 30 feet thick. You can also see some signs in this photo that soon after we arrived, the summer melt was really quickly fully underway. So on the surface, you see some of what look like little lakes, and they're actually melt ponds. And so these form from pooling of the melting snow and ice as the melting is occurring throughout the summer. This is another perspective of our flow where you can see the ship again and lots of these melt ponds on the ice, and they can actually be really sometimes quite deep. So for my work and much of the ice team work, we went on the ice every day to make observations with instruments and collect samples. And so this is a time lapse from one day when we're walking out to make some observations at one of our sampling sites. And I mean, I think this is fun too, because the landscape is really remarkable. I think being out on the ice, it often looks like another planet. There's all these different shades of gray and white, and green and brown. You can see on the ice, there's kind of some texture. We get these kind of hummocks from melting over the summer, also kind of ridging from the ice getting pushed together. You can also notice sometimes in here, there's little sticks that we're walking by, and those are kind of marking our paths, sort of like roads to where we're going on the ice. And this helps us avoid disturbing areas that we might want to use for observations. And when you're out here, it's often easy to forget that you're actually walking on top of thousands of feet of ocean, especially when you're doing it every day and it feels, you know, like part of your daily commute, just a little different. So as I mentioned, one of the two big things I was there to measure and to study was the albedo of the ice. And so I want to talk a little bit about what exactly the albedo is. So albedo is a really important term for climate, but it describes a concept that you likely already understand. So if it's a hot summer day and you're going to be out in the sun, would you rather pick the white t-shirt or the black t-shirt to put on? You'd probably pick the white one since you know that it's going to help you stay cooler, it's going to absorb less heat, you're going to be less warm. So the same concept applies to the Earth's surface. The darker surfaces will will reflect more of the energy, or less of the energy. And so I think I've said this the wrong way. The darker surfaces will reflect less, and so will warm more. Yeah, so all of the different covers of Earth's surfaces have different albedos. So like the metaphor with the shirt I just made, sea ice has a much higher albedo, and so reflects a lot more of the energy from the sun than the ocean. And this is particularly important for climate because it can result in a feedback. So as ice is melting, we're absorbing more of this ocean, and there's more heat absorbed into the ocean, and so we can melt more sea ice. And so you can see how this cycle can continue. So, and again, in this photo, you can see that the sea ice generally has this higher albedo, so it reflects more energy from the sun and stays cool, whereas the ocean appears very dark with a lower albedo, and so absorbs more energy and gets warm. But the details of the albedo of the ice also matter too. You can see also in this photo that on these ice flows, they're not really quite uniform. So we have these pools of water, the melt ponds, that are relatively quite dark, and there's also just areas of the ice that look darker and lighter. And so all of this detail really matters a lot as well for how the melt progresses over the summer. And being able to capture these details in models is key for how we project sea ice melt and Arctic warming in the future. So we would go out regularly to the flow to measure on a small scale the changes in the albedo over the same area. So in this video, I'm measuring the albedo at different points along the same line that we would go to on different days. And we want to understand both the details of the variability in the albedo in space, which is why we measure it at lots of different points, as you'll see us starting to in this video, and also how it evolves over time on a scale of days to many months. And so we'd come back to the same point and make these same measurements in the same way a couple times each week. The instrument I'm using in this video is called a spectrometer. And so this measures the albedo. And the way it works is that we first measure the energy coming from the sun. So we have it pointed upwards, and we measure the incoming energy, and then flip it over and measure the energy that's reflected. So in the basic sense, this just gives us a ratio, and the albedo, so we can understand how much is reflected, which is the albedo, and then also how much is being absorbed into the ice. So one way we do this is sort of bulk, where we basically just get a fraction like I just described. And the other is actually a bit more detailed, where it splits it up into different wavelengths. And that's actually what I'm doing here. And so you may be, you're probably familiar with the fact that light is made up of lots of different wavelengths. And so, for example, you can see that the ice is blue. So you can tell that it's not absorbing all the wavelengths of incoming energy in the same way. So these are really important measurements to make. And we also coordinate with them with lots of other measurements that are being done by some of the instruments that you saw in that kind of video introduction earlier, that are being done below the ice and also above it with helicopters and drones. And these help us understand our measurements and put them in the broader context. Yeah, I'm not going to go into detail on most of those measurements. There's many things beyond what I can describe here today. But one I do want to mention, one of the other tasks that we did was ice coring, which is what I'm doing here in this video. So this barrel, this red barrel, you can see it drills down into the ice like a normal drill, but it extracts this core, and which you can see in this, sitting in this thing on the ice here. And cores of ice are sort of like tree rings, and that we can use them to understand the history of the ice and its structure, and so how it's grown and evolved. And that's related to a lot of the other things that we're interested in, like the albedo. So many of my measurements focus on understanding the evolution of albedo in specific areas on specific types of surface cover. So this is a photo where on the left you can see there's some snow on the surface at the beginning. And I made measurements at the same location on 2 dates about a month apart. June 21st is on the left, July 29th is on the right. Initially, the albedo was 0.76. And so what this means is that 76% of the incoming energy from the sun is being reflected when it hits that surface by the ice and the snow on top of it. In the second photo, the albedo, as you can see on the slide, is 0.57, exactly the same location. So this means that it's absorbing almost 20% more of the incoming energy, which is actually quite a bit. An interesting feature of the flow that we were on for Mosaic was that we actually had lots of different little rocks and shells and sediment in the ice, which is not necessarily very common, but was a result of this ice forming near land. And it gave us a really exciting opportunity to observe how the ice evolves with sediment in it over the summer. So you can see, it's obvious in the second photo, you can see these kind of areas where they're a little dirty, and it's really got this topography, this kind of structure, these hills or hummocks. And this is where these areas of sediment have melted away faster. And that relates to, we can see in our data, a lower albedo. So where there's actually more energy here being absorbed than reflected by the ice. So that's something that's really interesting and exciting about for us in this data. I just want to hint a little bit at some of the results that we got that we're really excited to be digging into. This plot shows albedos averaged over our different measurement areas all throughout the summer. So going through June, July, August, from left to right on the plot. If we had albedos all the way at the top, that would mean that all of the energy is being reflected. Albedos all the way at the bottom would mean that all the energy is being absorbed. So you can see that the albedos of the ice, of the sea ice, are on average always kind of in the middle between these extremes. And as the melt progresses, it generally gets lower, but the really interesting thing is that it's not actually always in one direction. There's lots of small changes day to day that affect the progression of the albedo and also the melt of the ice. And so this is really what we're excited to use this data that we collected to try and understand. So the measurements that we made of albedo help us understand a lot of aspects of how the ice is melting in terms of on top, and to a degree also how it's melting on the bottom where it's meeting with the ocean. But we're also really interested in understanding how the ice is melting at the sides, where the dark ocean in these leads, like you can see in this photo, that have really low albedos are absorbing more heat. So in this photo, I'm making measurements of the heat that's in the upper part of the ocean, where we get a relatively fresh layer that forms from the melting snow and ice surrounding it. So the low albedo of the ocean, as we talked about, means that it's absorbing proportionally a lot more heat than the ice. And so though you can't necessarily see the heat, I think in this video, it's surprising to kind of see how much there is going on. And you can see lots of kind of green in this video, an indication of things living in the water. This area is actually really very productive. And also sometimes in this video, maybe you can see it if you kind of squint, sometimes you can see a shimmer in the water. And what that indicates is this changes in how salty the water is and how warm it is. And that's indicating for us where we have these layers that are fresher and are building up a lot more heat. So these are profiles of measurements that I made of temperature on 2 different days. And so what these are showing is the temperature of the water above freezing. And so the freezing point would be here. It's actually not quite 0 degrees because of salt in the water. And so all of these values that are more than that are above the freezing temperature. This is looking at depths below the water down to about a meter. So that's about the scale of that video was over. And so it may not seem that warm. We see maximum temperatures here of about 1 degree Celsius above freezing, but all of this is heat. And so that means that that has the capacity to melt ice that's nearby. And actually over the course of the summer, especially at the end, we were seeing rapid melt, inches a day from both the bottoms and the sides of the ice. And it's really interesting and important to make these observations for how it melts the ice. We want to understand how heat is building up in the ocean and how it changes over time. But it also is affecting lots of other processes other than just the melt. You saw that green tinge in the water. So it's clearly having some implications for the ecosystem in the Arctic. And also impacts how the ocean interacts with the atmosphere. So in this photo, there's colleagues from the ship, from all of the different teams that were coordinating to measure different properties and processes that were happening in the ocean in these leads throughout the summer. And we made measurements in lots of different areas of open water at different times to try and capture how it varied. So in this video, you can see there's lots of kind of chunks of ice. I'm out on the kayak making measurements kind of near the other edge. And this is another one where you can see that on this day it was really sunny and there's this really wide open water area. And so here we actually saw more heat based on these differences. And so that results in faster ice melt next to this area. We were also really interested in looking at how things change in the broader area. So we're making all these measurements on one little piece of ice in the Arctic, which is really amazing data that we definitely need, but it's important to kind of step back and look at how these measurements fit into the broader context. And one way we do that is by doing measurements and taking imagery also from helicopter flights, which you can see an example of from this summer here. And they help us see the ice in a different way. So you can see in this video ice of lots of different shapes and sizes, lots of different ponds with different colors. So there's a lot that's happening that kind of what we observe on the small scale on the flow kind of scales up to make these impacts on the larger scale in the Arctic. So for me, these observations that we're making on the ice and in the leads right near it are specifically motivated by the needs of models to make better projections, as I mentioned at the beginning. So sea ice components of these models, there's one called SICE, which is what I use that is shown schematically here. And they actually represent ice relatively realistically in a lot of ways. They can represent a range of sea ice thicknesses, and they represent how it's growing and melting and getting pushed together by the ocean. But of course, there's many things that could still be improved in these models and are actually lacking necessary data. And that's what we targeted during Mosaic. So just for example, the two of the things that I'm interested in using are observations, for example, our observations of leads where we can look at sea ice melting from the edges. And we're going to incorporate this into the model to update our parameterization or our representation of ice melting at the edge. Also, all these measurements that we made of albedo throughout the summer are going to be used to update the model for how they represent the albedo. And hopefully specifically work towards including sediment, which we got to observe in the ice this summer. And these could both have large regional and kind of climate scale impacts. So I just want to mention, because people always want to know, we saw a lot of polar bears actually during this time when I was on Mosaic. During the period that I was there, I think we saw them almost 30 times, which was very cool to get to see them, especially because we were always careful to be very safe and to not be on the ice at the same time as them. Polar bears definitely rely heavily on the ice to travel and hunt, and we saw them doing those things, and so we stayed away, especially for those reasons. And polar bears in different areas are definitely being threatened by the changing climate to different degrees, but fortunately the ones that we saw all seemed healthy and well fed and to be thriving. Yeah, and sort of similarly, I want to end my talk on a little bit of a note of hope. So these are two photos towards the end of summer from year-long expeditions in the Arctic. So the top one is from 1998 from an expedition called Sheba, and the bottom one is from 2022 from Mosaic, about 20 years apart. So there's a lot of things that were different between these expeditions and also between what was observed, but there was also a lot that was still similar, and perhaps even more that was similar. And I think probably a lot of you are here, I would guess, because you're aware there's big changes in the Arctic, and of course this is true. I don't want to discount that, but I think it's important to remember that the Arctic is still the Arctic. There is still going to be ice that is formed there, and we have reason to believe that the Arctic is quite resilient. And we're really hopeful that it can rebound well if we adjust the current trajectory that we're on as a planet. People often ask me if it's depressing to study the Arctic, and certainly there are things that concern me, but there's also a lot to be inspired by and hopeful about, and we saw a lot of this during Mosaic as well. So just two little examples of things that really excited me during Mosaic. The first is really more specifically for me as a scientist. We observed very high albedos on relatively thin ice late in the summer. And so this is kind of a sign of resilience of the ice, that it helps the ice last depending on the conditions further throughout the summer. And the second was this video, which I'll play it again, of these polar cod that we saw finding refuge in a crack on the ice. I'm not a biologist, but I understand that polar cod are a really key part of the Arctic food chain, though they're rarely observed. And so just seeing them in this crack was kind of a sign of the resilience of the Arctic. And yeah, this is a place that's really worth protecting, and it's still in our power to do so. So that's all I have for my presentation. I guess it was a little short, but that means that we have lots of time to discuss, and I'm really excited to hear what questions you guys might have for me.
Thank you very much, Maddie, for teaching us lots this evening with some great photographs and videos and sharing about your amazing summer. And so, yes, questions. If anybody would like to ask questions, you can certainly raise your hand in the participants menu or put them in the chat or just start speaking. I will start with a couple. And one is, can you talk about maybe concerns about safety being on the ice? I mean, I know you mentioned, the polar bears, etc., but ice thinning areas of the ice, were there concerns about falling through the ice? Were there concerns about getting lost when everything looks very, you talking about this?
Yeah,
there's a question that's coming right through.
Danger falling in the water. Yeah, that's really on the same note. Yeah, I mean, these are good questions. And I mean, the safety concerns actually vary a lot throughout the year. So in the summer when we're there, the ice is thinning, it's melting. We obviously have these melt ponds, which are, you can see even in this photo, which are indicating that the ice is kind of melting away there, and it's often thinner underneath that. So we had a number of different ways that we are safe. I mean, they had a very comprehensive safety kind of approach on the ship, and obviously had lots of people that were specifically hired for logistics, and so their kind of jobs were to keep us safe and go out with us. So they would often act as the bear guards, although sometimes scientists would as well. So we would take turns doing that. The job of bear guards is primarily actually just to keep lookout. I mean, we do carry a rifle and flares out onto the ice. The bear guard will have those, but I mean, really the goal is to see the bears and just leave the ice when they're nearby. And that was almost, I think that was always the case. There were flares that were used sometimes from the ship to get scary bears away. But yeah, the idea is that the polar bear guards are lookouts to keep us safe. And in terms of falling in the ice and kind of thin ice, I mean, one of the good things during the summer is that you can see it. When ice starts to get thin, it does start to get darker. I mean, this is related to the albedo I was talking about. You can see the ice being thinner, and so you have to be careful to avoid it. But we also, regardless, always wear flotation on the ice, and there are like kind of different levels of flotation. So sometimes we would have just these flotation suits. The brand is FXR, so we called them FXR suits. And those have flotation built into them, but they also keep you warm. And if you're really somewhere that you're in danger of falling in, particularly when I was working in the leads from the kayak, I would wear a full survival suit. So that's like a dry suit. So if you were to fall in, you would truly stay dry and warm and very safe. The concerns in the winter are very different because it's often much harder to see. And so these roads that we had during the summer, I mean, they're much more casual. It's pretty easy to see where you're going most of the time, unless it's a bit foggy. But in the winter, there really are a safety need to be able to see where you are to get back to the ship sometimes, and just to be aware of your surroundings. And also in the winter, it can be harder too because snow can cover up hazards like thin ice, whereas in the summer, it's more hidden. Was kind of a long answer, but yeah, there's different ways we keep safe out there.
And we've got a question from Rita about how does the ship get attached to the ice?
So the ship, I mean, so you can see in this photo by the end of summer, I mean, it's a lot more open, so you can see that you might actually need to attach it. But when they froze it in initially, I mean, there is ice all the way around, and so it's just kind of a matter of stopping the ship, turning off the engines, and then it will just it'll just drift along with the ice. And so for most of the year, that was what they were doing. When I got back on the ship at the beginning, this is a photo from the end of summer. At the beginning of summer, because things were starting to open up more with the melting, they would use kind of a combination of anchors from the ship to the ice. I mean, like you would anchor it to the bottom, but instead just putting anchors into the ice. And I think they use those still throughout the year. And then also they would use the engines, the thrusters a little bit to push into the ice to keep it kind of aligned with where we want to be.
Peter Neidhart has hand raised. If you'd like to unmute yourself. Sure.
Hi, can you hear me?
Yes.
Yeah. So thanks, Maddie, for the presentation, and appreciate how you added all the graphs and the videos to it. Very interesting. My question is about your manual measurements of albedo with regard to what's possible by satellite remote sensing. So I'm curious how manual measurements supplement, complement, or dovetail with satellite measurements, and especially because a satellite can cover presumably tens or thousands of square kilometers in the time that it takes you to walk out there and do your thing with your instruments. So how does that work together, and what are you able to do that satellites cannot do? Thank you.
Yeah, that's a really good question. And actually, I mean, I didn't mention it, but we were measuring during this expedition albedo on all these different scales as well. I mean, so there are some people doing it with drones. So you're flying just, a couple times what you might be above what you might be walking, and then sometimes from the helicopter. And then of course there's satellite measurements, although their satellite measurements are limited by clouds in the Arctic quite a bit of the time. So I mean, that's a challenge with, the nice thing about being on the ground is you can always make a measurement regardless of the weather. But I mean, one of the big questions, all of these other approaches where you're above the ground, you are really missing a lot of the small scale detail of what's happening, from one kind of area to the next, just as you're walking along. You could see in those videos from where we were walking that things really do change quite a bit. And so when you have these measurements higher up, you're integrating, kind of averaging over these much larger areas. And so we can really get the fine scale detail to understand the processes that are actually driving the change. And that's what we need in the models. I mean, those kind of averages that you can get from satellites, remote sensing, are really important to understand kind of average changes. But in order to understand the processes, we really need more detailed observations. And that's what we get from being on the ground. And we can really match them up with, specific observations like ice cores and things like that.
Question from Jane. While you were on the expedition, were there any moments with findings that were broadly exciting?
Oh, that's a good question.
Especially exciting.
Yeah, I mean, there's lots of moments that are exciting for a different reason. I mean, some of them that are like very personal and some of them that are more broadly exciting. I mean, there were some things that felt kind of fun as like a whole group. I mean, they were doing a lot of, so from the ecosystem side, they've been trying to catch fish all year to kind of look at what the fish have been eating and understand this really ecosystem perspective. And they'd been trying for a long time. So I remember when they caught a fish and that was very exciting, something we celebrated. I mean, the other things are sometimes hard because this data takes a long time to analyze. And so some of the things that we think are exciting might like take a while to know that they were happening. But I think like observing like when these melt ponds like form in like one day, really. I mean, like it's not quite like that, but there's just like one day where it looks like it's snow covered and then one day there's melt ponds, and that you wake up and you're like, wow, you feel like you've been looking at your backyard and it's the same every day and then suddenly it's different. And then sometimes, I mean, you know, some of these ones that would just get huge and then they would drain. I mean, and those aren't necessarily the scientific findings that are going to be exciting, but observing these events and knowing that we're capturing them with all of these detailed observations is really cool, because it means that, you know, we're seeing these big events happening. We also have the data to describe them, which is the point.
On that note, can you talk a little bit about the scientific process? I mean, looking at this expedition being something that was decades, the culmination of decades of planning and the big international work to get this together. Where does it go from here? Can you talk about that next process of, you know, you're talking about you're still getting into the research now. How long do you expect this data to be relevant to be continuing the scientific discussions?
Yeah. I mean, so I mentioned right at the end this picture from, let's see if I can go back to it, this picture from this other expedition, Sheba, which happened in 1998. And we are still using that data from that expedition in 1998. That, I mean, these really amazing data sets, they have legacies that are, you know, decades. And so Mosaic was planned over a long period of time with the intent to be a landmark data set that will be used for a really long time. And I think particularly because we are making so many measurements of all of the different things that were happening. I mean, what's happening in the atmosphere, what's happening in the ocean. I think really understanding how it all changes together is what's needed. And so I think this data is going to be used for a long time. And on the same note, so I mean, all of the planning that went into this was very detailed to try and kind of make sure that we're making all the right measurements. And so they had a very detailed plan of all the data that was going to be taken in the same way throughout the entire year. And so now is kind of when we go back and start analyzing those things to bring them together. And I think, you know, a lot of this takes a long time because there's just so much that's being collected. And so in some ways we're still like, you know, just doing QC, like just cleaning things up. Although, you know, we can still see some of the results as well. But I think in the next few years, we'll really start to see a lot of the impacts of this work on our understanding.
Great. Lynn Carlin has a question about the temperature range, air temperature range in the summer.
Yeah, it's kind of amazing. And the air temperature in the Arctic in the summer is almost always right around 0 or 0 Celsius. So about, you know, freezing, 32 Fahrenheit. It doesn't go that much above. I mean, at least where we were, it rarely went above or much below. We saw a little bit of rain, a little bit of snow. But yeah, it's like remarkably stable during the summer. And it starts to feel warm. I mean.
Did you find any unusual stuff in the ice, like parts of old wooden ships or plastics? And I know in previous discussions this fall, we've spoken about, you know, denim fibers being now found in the Arctic, et cetera. What
Yeah, so there's definitely some interesting things about our flow in that I think I mentioned this ice had formed near the coast in Russia. And so we didn't find any of these kind of human relics like you suggested, but we did see a lot of shells and rocks and other things that are really suggestive of that it came from the coast. But I mean, one of the projects was measuring microplastics. So they were taking samples from the ice and the water, which they will be kind of filtering and looking at the amount of plastics, you know, which can end up there, you know, from all over the globe throughout the year. But those were not being analyzed on the ship. So I actually don't know what they were finding, but I mean, it is we know that microplastics are making it into our water and our ice around the globe. So though I don't know what the levels in the ice were, I imagine that they were finding indication of plastic in both of those.
Can you talk a little bit about the interaction of the different scientific crews on the ship, in the sense, I mean, you spoke about the different groups, but also, you know, different nations that come in with different ideas, different agenda items. Were you collaborating together? Was everybody independent doing their own projects? Were you helping each other out? How does that?
Yeah, so I mean, there's kind of just some different ways. So we are really divided up into these sort of topic teams, and partially just for like logistics of having a smaller group to coordinate with on the day-to-day. And within these teams, there's sort of like a weekly schedule of specific tasks that need to be done. And some of those were really broad to the kind of the general, like they may not be your scientific research project, but we had, like, for example, the coring, like we took ice cores in the same place every week throughout the year. And so there might be specific people working with that. We knew that was like an important thing to capture for the like the sea ice community and the climate community. So everyone did that, kind of pitched in for that. So we kind of had these specific teams that we were working on, but we also, as a scientific party, would meet nightly to kind of talk about the plan and kind of some scientific results. And so we would look at, you know, we would kind of interact with each other and see what other kind of big gaps there were. And so sometimes have these more collaborative days as opportunities arose. So for example, when we were doing a lot of the lead sampling, that was maybe not one of these like core things that we needed to measure, but that we saw really important opportunities to collaborate and understand the kind of bigger Arctic system. And so that we had different people from different teams doing that together. And those are the things that I think were really the most exciting too, because you get to see how we can kind of collaborate across different disciplines to better understand how things are changing.
And building on that, Jane's question here in the chat, for all the research areas covered, was it evident to most what questions were not addressed?
Yeah, I think, good question. I mean, I think one of the things about fieldwork is like you always come back with more questions than you left with, and that's a good thing about it. I mean, that's what keeps us going and excited to be doing this work, is that you can't always get everything. I guess it's hard to say what questions were not addressed. I mean, I think there were some things that we saw that somewhat surprised us. I mean, seeing so much dirt in the ice was kind of interesting. I think is something that we'll look into more. Also, just some of the ways that the different areas of ice change in really different ways is really interesting. I can't speak to the other kind of what the atmospheric scientists would say, but I think that there is definitely more questions that are brought up from this expedition to answer in the future than necessarily we can answer.
Question again from Peter. When you're talking about the ice cores that you were taking and the aging, were you able to determine the age of the ice in the cores? So, for instance.
Yeah, so we don't have methods that we necessarily use to know exactly how old the ice is, but we have a couple different indicators, ways to tell us how old it might be. So, I mean, so a lot of this ice had grown kind of over the last year. So it's what we call first year ice. It's, you know, within a year old. And that has a very specific like structure of what the ice looks like. And also when we make measurements throughout it of the temperature and how salty the ice is, there's very characteristic ways that it looks. They look very different than ice that had survived a previous summer and is maybe 2 or 3 years old.
Hey.
But it is kind of harder to determine how old exactly once you get kind of beyond that 2-year mark, how old the ice is. But one of the real benefits of being over here over the whole year is that a lot of the ice that fell into this newer category of being a year or slightly older, we'd actually been observing it that whole time. And so we knew exactly how old it was because we'd seen when it had grown. And so we were able to kind of relate the changes that we're observing to what had happened in the past. And so telling that history is the really exciting part.
How does the greenhouse effect change how the ice melts, and how does that play into the positive feedbacks that you previously mentioned?
Yeah, so I mean, I think a lot of the impact of the greenhouse effect is the kind of large scale warming that we're seeing on the Earth, and particularly the fact that the Arctic is warming more is driving the melts of the ice. But I think the other component of that is that this greenhouse effect is also, we're dumping more CO2 into the atmosphere, warming the atmosphere and also warming the oceans. And so the ocean is also really a big impact on how the ice melts. And so it's really just primarily through these temperature changes, both in the atmosphere, but also in the ocean, which is accumulating a lot more heat over time, that melts more ice and also causes it to grow more slowly in the winter. And so that becomes a positive feedback primarily in these other ways, in that as there's less ice, it has a lower albedo, and it's not slowing that heat transfer as much. But as far as we know, as far as I know, there aren't any specific feedbacks of the ice into the greenhouse effect, although it does have other impacts on the kind of climate of the globe.
Do you, on that note, are there concerns about the elements that are in the ice, that when the ice melts, releasing elements into the water, that you end up with the methane and carbon cycle?
Yeah, that's like a bit beyond my expertise, but I mean, there is some, what we call multi-year ice that is many years old, but the good thing is that, I mean, most of this ice has formed within the last few years. So unlike like ice sheets, like on Greenland, or permafrost, like along the coast of the Arctic, there's not like long-term carbon storage in the sea ice, because it's all formed in relatively recent history. So we're not going to be releasing things that have necessarily been there a very long time. The timescales of sea ice are much shorter, which is also a positive thing for us studying sea ice, because it means that it has the capacity to be a lot more resilient, because it does grow on these shorter timescales, that if climate is to kind of stabilize or become kind of reverse some of the climate warming that we've had, that the sea ice can rebound more easily, because it does grow on these relatively short timescales compared to ice sheets.
And can you talk a little bit about what it is like to be a female researcher on some of these expeditions? The New York Times profiled Mosaic specifically back on October 12th for what it's arguing gender inequality and dress codes that were applied to women aboard the ship. And can you just speak a little bit about that experience?
Yeah, so in planning the expedition, I mean, Avi made a very good effort to kind of have more diversity in leadership, and as well as the people on board, which is, I mean, really awesome to see. On the leg that I was on, we had kind of 50-50 women and men, which has not always been the case, especially with such kind of diverse nations being represented. But of course, there's always a challenge in working in really diverse environments. I mean, I guess what I want to say is this issue that arose that was kind of profiled, I think, was related to a lot of different cultural expectations and kind of working in this more diverse environment. So, I mean, I guess the other point is that there's still a long way to go in making these different scientific research environments really equitable and safe for everyone. I mean, I want to be clear about that, is that there's still improvement to be done. And so so everyone I worked with on the ship when I was there was really great, and I think that they've kind of done their best to kind of find the middle ground of working with lots of different nations together, but there's definitely still improvement to be done in making women in field science feel more welcomed and safe.
Thank you, Maddie. And
Yeah.
you just mentioned sea ice and sheet ice. Can you please describe the vocabulary of ice, so the different types of
Yeah, sometimes it's hard to not just throw these words around. This is a good question. Yeah, so sea ice, maybe I should have really made this explicit at the beginning. We're looking at ice that is forming in the ocean. So sea ice means that it's ice that is actually forming from seawater, and that's what really defines it. So I guess this is really distinct from ice that has formed on land and is, fresh, so it doesn't have any salt in it, but also, so I guess icebergs are one thing. So in Antarctica, we have this ice that's covering land. We have these huge, massive glaciers, and sometimes pieces of this fall off and these big chunks of ice fall into the ocean. And so we have ice that's in the ocean, but those icebergs are not sea ice because they've actually formed on land. So Antarctica and Greenland are both, we call them sheet, kind of ice sheets, because they're these big areas that are have ice over them, but they're essentially also glaciers, which are, happen all over the globe. We have glaciers here in Washington and, lots of different places with glaciers. But so sea ice is specifically what forms in the ocean.
Great, thank you. And I think that's the last question I'm seeing right now, but if anybody else wants to ask a question, either raise a hand or put it in the chat. I'll give you a couple moments to do that. So Maddie, in the meantime, can you just tell us what's now? What are you doing? What are you doing now? You've got all this data. What's what?
Oh, there's so much to do. It's so hard to know where to start. Yeah, so a lot of it, as I mentioned, is just like cleaning up the data. Though I've already started working with it, part of this big collaborations is to make our data sets accessible for others so that they can work with them too, and to kind of archive it for these decades of science that are going to happen in the future. So that's the current effort. It's really important, not always the most glamorous part of it. The other part is we do have a lot of science questions we're excited to look at. So a lot of the kind of albedo data that I mentioned, we've been working with, and we're working on some papers to describe what we saw and what we think is really interesting about this data. And then I'm also as I mentioned, working with the climate models. And so some of these things that we saw that we think were important on Mosaic are not currently represented in how we make projections for the Arctic. And so we're working on doing some new kind of things in models that will help us better improve our projections for the future. And so those are two big things. Yeah, I don't currently have any plans to go specifically back to the Arctic, but I certainly hope to again in the future. That's a pretty special place, and I feel pretty fortunate to get to work there.
Jane just asked a question about whether you're planning to go back on any further science.
Oh, I didn't even see that. I definitely will in the future. I don't currently have any planned, but yeah, I plan to keep doing polar fieldwork. I've gone to the Antarctic once as well, and it was cool to get to see how those compare. So we'll see where I go next, but I'm definitely hoping to do more research in this area.
Great. Well, there are no further questions. Thank you so much for joining us, and all the way from Seattle, and really appreciated you being very enthusiastic and sharing your expertise.